Good morning to all of you. I am Ashwin Joy. I am an assistant professor in the Department of Physics, IIT Madras. I will be teaching this course on statistical mechanics, and just to give you an idea in a nutshell, statistical mechanics is a subject which deals with large degrees of freedom, such as the gas in this room at temperature T or a solid at room temperature. And what it basically does is it uses the information available in the degrees of freedom, such as the momenta of particles or the spin of particles, and gives us answers to such as what would be the thermodynamic property of this matter at equilibrium. Such as if you ask what is the heat capacity of gas in this room at temperature 300 Kelvin, statistical mechanics will give you an answer. If you ask what is the magnetization of a Curie solid below its transition point, statistical mechanics will give you an answer. The tools used in statistical mechanics are different from the tools used in classical mechanics, in the sense that here we have a probabilistic interpretation of the system, meaning that we do not really time evolve a set of equations deterministically as you would normally do in classical mechanics. What we normally deal with here is basically the distribution functions, which have a natural beautiful meaning at equilibrium, and then we proceed with these distribution functions and try to answer thermodynamic properties of materials. My course will have 3 chapters, and these are the chapters that will give anybody looking for a working knowledge or looking to acquire working knowledge in statistical mechanics would greatly benefit. And I am a strong believer that if you start off with probability concepts and grow slowly from there, you can very efficiently and in a short period of time develop powerful postulates of statistical mechanics, and then using these probability concepts and postulates, you can tackle any problem in statistical mechanics, at least in equilibrium statistical mechanics. So, yes, the content of the course will be revolving around only equilibrium statistical mechanics. We shall restrict ourselves to venture into the domain of non-equilibrium statistical mechanics. For this particular course, we will start off with simple probability theory, where I will start off with examples in the context of discrete random variables, and then after solving some problems we will discuss continuous random variables. But these are very important because the molecules of the gas in this room basically have momenta, which is a continuous random variable. And when you are dealing with random variables and you have a probabilistic interpretation, you require moments of random variable, because you do not have a exact time evolution of these random variables. So, I will discuss how to compute moments and higher order moments of these random variables using a very efficient technique which is called a generator of moments, and we have a name for them. We call them characteristic functions. And after this we will discuss some very important concepts in statistical mechanics, namely the central limit theorem, maximum entropy principle, and so on. After this I will discuss the postulates of statistical mechanics, which is basically the well known ensembles that around which we live, such as the microcanonical ensemble, the canonical ensemble, the Gibbs ensemble, grand canonical ensemble. All these ensembles are used in laboratories, experiments, and in numerical simulations of matter, and they are very important. So, we will spend a great deal of time understanding these ensembles from microscopic descriptions. I will then discuss in the final chapter concepts of quantum statistical mechanics, and this is very important because most systems in the limit of low temperature and high densities are inherently quantum. They are not classically behaved, such as electrons in a solid. And these electrons are also known as electrons in the Fermi gas, and their behavior is very different from electrons that we look in for example this room classically. And the differences arise primarily because of the counting statistics, which are fundamentally different between electron gas at equilibrium and electron gas in a solid. So, I will discuss these current counting statistics that is used in the in quantum mechanics. And in this context, we will be talking about electrons in solids, and that is an example of a Fermi gas. I will also discuss photon gas in a cavity, which is an example of a Bose gas. And these two different systems obey different types of statistics purely because of the underlying symmetries that come from quantum mechanics are fundamentally different. We will discuss all that. And I will finish by showing a beautiful correspondence between classical statistical mechanics and quantum statistical mechanics towards the end of this course. I will show that how one can seamlessly develop or obtain classical statistical mechanics as a limit of as a high temperature low density limit of quantum statistical mechanics. So, that would be the towards the fag end of this course, and this is basically the outline of the entire course. I will also take this as an opportunity to introduce you to my teaching assistant for this course, Mr. Sachin CN. He happens to work with me for his PhD.
Hello all, I am Sachin. I am the TA for this upcoming statistical mechanics course in the NPTEL series of lectures. I am a doctoral fellow in the IIT Madras. I am in my second year of the PhD. I am working under Professor Ashwin. Basically, I am working in the field of non-equilibrium statistical mechanics. Currently, I am working on active glass forming liquids. I will be the TA for this course, and I will be responsible for all the assignments and also the doubts regarding the lecture that has taken place on that particular week. I will be available along with my professor in the chat room discussions for any of your queries which you are put together in the discussion forum, and we will make sure that your queries will be answered within very short period of time. Hope you will enjoy the subject as a whole. Thank you.
A few important things regarding organization of the course. We will be doing some problems in every class. So, that would be in some sense a hands-on experience in solving problems using concepts developed in the course. So, you will see how I solve the problems, and then at the end of the lecture I will also leave some homework problems for you to solve. They will be ungraded, but every week you will get a set of problems which you are supposed to solve on your own, and we will also upload the solutions once the deadline of submission of solutions is over. So, you will not be left in dark as to how to solve this problem eventually. You will get detailed solutions from our TA, and if there are 12 weeks, there will be 12 assignments in total, which you are supposed to take home and solve and submit before the deadline. In the end of the course, there will be a final examination that will carry a significant percentage of your overall evaluation. So, I suggest that you stay focused and you discuss all your doubts as and when they come to you with my TA. We will both be very happy to be of any use throughout this course. So, let us know if you run into issues regarding problems. We will be available in chat room discussions, and we will take care of it. Thank you.